Well, good afternoon. How'd lab go last night? Pretty much everybody check out? Yeah, more or less. Yeah. There's a couple of things I wanted to talk about obscurities. One is that at least one group spent a while trying to figure out why their system wouldn't toggle, wouldn't clock, and it was because they misspelled a clock. It's easy to do. Always, when you get some obscure error, what the hell is going on? First thing you want to do is bring up the warnings and do a search for implicit net. You want to search for the word implicit. If you find any signals which are implicit nets, then it means you didn't declare them or you misspelled them. So if you lowercase the clock signal rather than uppercase it, for instance, this will say implicit clock 50 with lowercase, and then you go, ah. But check that. If you get obscure errors with another one I've done often is define an audio output and forget to declare it, and it defaults to a 1-bit wire. And so your audio output is shrunk from 16 bits to 1 bit. And it's the least significant bit. And so if you turn it up really loud, you can just hear this. So it's worthwhile doing. The second is, I was fiddling around with compilation today and realized that the number of DSP blocks that the compiler was reporting is not the same number as I had told you. And I tend to believe the compiler. So I went back and checked the documentation again, and it turns out there's a CycloneE and a CycloneSE. And I gave you the numbers for the E, and we have an SE. So the correct numbers for the number of multipliers is 87 multipliers for a total of 174 18 by 18s. That's not enough to do a 16 by 16 drum. Therefore, to get enough to do a 16 by 16 drum, you have to put at least you have to use one multiplier for at least 2 nodes, which means you have to serialize over at least 2 nodes. So you could pick 2 nodes that are next to each other. Instead of doing them in parallel, you do 1 then 2, and that would give you enough multipliers because you can reuse it in the state machine. There are just under 400 M10K blocks and 480 MLab blocks. There's a question about how you instantiate an MLab block. You can, probably the easiest way is on the line of Verilog where you declare the register array, which is the memory itself. You use a synthesize comment and give a synthesize directive on that line. Like we talked about, what, 2 weeks ago? You put a synthesize directive on the line, and that'll force the memory into MLab blocks. But one MLab block is 32 by 20 words. So 1 week from today, we start Lab 4. Oh my God. But in the next week, I suspect that many of you are going to be parallelizing your code. And it is essential to build a timing diagram to do this. Probably some of you have already started doing this, where you lay out cycle number cycle number horizontally, the march of time, and you say, okay, what could we do during cycle 0? Well, we could, let's call this the UN block and the UN minus 1 block. We could do a read here. We could do a read here. Actually takes 2 cycles to do the read, right? Because there's 2 cycle latency from an M10K block, if these are M10Ks. So a read takes 2 cycles. What could you do during that cycle? Maybe you could do something else. Maybe you could start some communication. You could load a register, load neighbors. You could load neighbors. Once you get here, then you could read something else. You could shift, but you need to lay out what every piece of hardware is doing on every clock cycle in your state machine. Otherwise, you will never keep track of it. Since the FPGAs are fine-grained parallel, you may have a dozen different things that can happen in the same cycle, but you can only use the same piece of hardware once in the cycle. So there's no substitute for laying this out and trying to then, once you lay it out, try to interleave it as much as possible to minimize the overall length of the sequence. Are there any questions about this, about parallelization or approaches? Who's going to do a column? 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 Who's doing blocks? Who's going to buy another bigger FPGA? Yeah. So, do you want to hear more about this? What do you want to hear about? So there's a summary is now linked up in Lab 3. The Cyclone 5 handbook has all the data, but it is 1,000 pages long, so I figured I'd abstract out the one table that made the most sense. What do you want to hear about Lab 3? Nothing? A couple of people yesterday were saying, well, MATLAB doesn't sound like the model simulation. You gotta make the sampling rates the same, folks. Apparently I need to say that. I didn't think I needed to say that, but apparently I do. And the results are not intuitive because your brain does not scale time well for audio. You can't remap. You can't do dynamic warping in your brain, apparently. So you got to get the sample rates to match. So if there's no Lab 3 questions, I am going to start on Lab 4. And I did a little bit last time. I'm going to do some more. I did build a Mandelbrot solver on the HPS just to see how fast I could move pixels across the boundary and to find out how well floating point worked relative to fixed point. In this case, 32-bit fixed point. And so the time to beat is going to be the time I could make this thing execute on 1 HPS. I managed to get it down by going to fixed point arithmetic down to 2.02 seconds, 428 fixed point. And by detecting circular regions, what's the biggest circle you can put into this region? What's the biggest circle you could put into the cardioid? I could get it down to about 0.85 seconds. And the reason there's such a large ratio, 2.02 going down to 0.85, is that those regions are where the number of iterations per point is maximum. And so if you can just not calculate those, you win big. So the cost of not calculating them is that for every point, you have to do a check to see if the point is inside two different circles. That has an overhead, a couple of multiplies, 4 multiplies. But overall, it wins slightly over a factor of 2 in compute time. So someplace around a second is the number you have to beat. If your code only does as good as my single processor HPS code, you will get essentially 0 on the demo. You might get 5 points if the mouse works well, but you have to do better than that. Because I'm giving you the code, right? So this will say, this implies that you're going to want to build parallel hardware for doing the iteration for each point. And as I said last time, the iteration is going to be of the form that Zn plus 1 at time n plus 1 is going to be z squared of n plus some constant c, with z0 equal to 0, and c being the well, let's just make it I plus jy, the coordinates on the screen of the point you're calculating. So you're going to form C. You're going to scale VGA coordinates into the region +1 to -2 and plus I to minus I, and the aspect ratio is not bad. So that's 3 by 2, and 640 by 480 is 3 by 4. So this is the aspect ratio fits fairly well on a VGA screen. Any value outside of these is guaranteed to diverge and therefore be outside of the Mandelbrot set. So there's no need to actually compute them, right? Right. And in fact, you can show that if at any time the magnitude of z is greater than or equal to 2, that the system diverges. And therefore you can stop the calculation on that point. Now, in reality, what you're going to do is square both of those so that you don't have to take a square root to get the magnitude. And of course, since many of the points interior are never going to diverge, you have to have an ending criterion. And I believe that the spec on the lab says you have to be able to choose what the ending criterion is, and it's going to be some number of iterations. It's handy for testing to be able to set this interactively, because if your solver is slow, you don't want to wait 10 seconds every time. So you could set Nmax to 30 for testing and 1,000 for production, for instance, if you have the ability to change that interactively. You're going to want to do that for testing, not only because I'm telling you have to do it, but because you're going to want to do it for testing. But we're going to test you against an Nmax of 1,000. So if after 1,000 iterations the system hasn't diverged, you say, I believe it's never going to diverge. That's not true, but that's an approximation you're going to use. And as usual, for complex code, the MATLAB is very terse. Let's see if I can. So this is the whole code to plot this thing. Actually, this is not plotting the whole set. I zoomed in on a small region. That -2, 1, -1, 1 would be the whole set. This is already zoomed to a tiny little region. And I set the termination to 100 because I was testing. And we need to generate some integer indices because that's what MATLAB likes. So the x-index and the y-index variables are the integerized versions of the space we're going over. And then we just blast through the iteration, starting with z equals 0 and n equals 0. And c equal to the complex number. I've never really cared for MATLAB's concept that I can be an arbitrary integer or it can be it can be the square root of -1, but okay. And so we just do the iteration exactly in the form that we have it up there. We count the number of iterations that have been done, and if we're still less than 2 and we're below the termination, we keep going. In the end, we're going to make an image array, which is the log base 2 of the number of counts integerized. So there's only like 10 different unique numbers there because there's going to be between 1 and 1,000 iterations. So the log base 2 is going to be between 1 and 10. We use this magic image scale on the array, which turns any array into a picture in MATLAB. And I like the color map summer, so that's what I chose. So that's all there is to it. Now the C is a little homelier because C doesn't know anything about complex numbers. And the Verilog is, of course, yet even more awful, but it's not that bad. We'll talk about the Verilog in a minute. Is there any questions on this, on the MATLAB before I? So the web page, the University Computer and UDP page, has, let's look at the optimized code. The problem with looking at optimized code is it's always more obscure. But unlike the nice vectorized MATLAB, I had to generate X and Y arrays by hand and then converted them to fixed 28 notation because I was doing everything in 428 fixed point. and was timing this by using the Linux get time of day call. It's very handy. And defined the center and radius of a couple of circles. Then iterate through the complex arithmetic, but I've got to have separate real and imaginary variables. First of all, we detect the secondary bulb, that's the little circle, and then the big cardioid. And we're doing this all in mult-fix 28 or in fix 28 notation. And if either of those is true, we just set count equal to count max and bail out of that, because we know that we're going to have, if we stay at that point, we'll do 1,000 iterations. We go into this loop, and the loop is going to give us some hints about how to do the Verilog, because we're doing a square operation, and then after we calculate the new n, we're doing the square root of sums of squares of the new n, new z, at n times n plus 1. Well, z real squared plus z imaginary squared is half of the arithmetic we have to do for the next iteration. So what we're going to do is we're going to calculate the real and the imaginary parts, and then we're going to square them and detect if we're above some fixed point value. But we're keeping these for the next pass through and using them where? Here, square and square, to calculate the next round of z squared. So we can have the arithmetic at the expense of clarity of the code, of course. And then this lovely chunk of code takes the log base 2 approximately. So I just shifted by factors of 2, which gives log base 2, and assigned what I thought were some pretty colors in 8-bit format. And you're going to do something like that in Verilog also. You're going to do a bunch of, you're going to find the location of the high order, so the log base 2 of a number, log base 2 of x is approximately the position of the high order bit. So if you have 1001, the log is about 3. How bad is this approximation? So if we had 1100, how much error would this one say? That's going to give me a log of 3. How much does this contribute? Turns out it's about 0.58. And no, I didn't do that in my head. I just memorized that. And the next bit, if it were a 1, would give me an error of something like 0.17. So you could add one more bit, but all you need is about 10 colors. So you may as well just use the position of the most significant bit as the log and just throw away the fraction. Question? I thought I saw it. Okay. So the C code starts to unravel the sort of high abstraction of MATLAB by exposing the complex arithmetic. So I suppose we ought to talk a little bit about complex arithmetic here. So what you're going to be calculating is Z real plus, let's call it J times Zi times Z real plus J times Zi plus C real plus C imaginary times J. And you crank all that out and you get that that the real part of this is the real times the real, so it's ZR squared and then you multiply these two together, and because they have J in front of them, you get a negative sign. J times J is -1 times ZI squared plus C real is going to be equal to Zn plus 1. Zn plus 1 real, and two times Z real times Z imaginary, 2 times Z real times Z imaginary plus C imaginary is going to be Zn plus 1 imaginary. The very next thing we're going to do then is to ask, is the magnitude of this Zn plus 1 squared greater than or equal to 4? And so we're going to then square Zn plus 1 real squared and Zin plus 1 squared, which is exactly the terms we need for the next iteration calculation there. Z real squared, Zi squared. So we save these for the next iteration. But that means we need a value for Z real squared and Zi squared for the first iteration, because I'm always using the value from the last iteration, right? So what is the value for the first iteration? I said earlier that Z0 is equal to 0. Right? Therefore, these are both 0 for the first iteration. If we were calculating a Julia set, what you said would be true. But we're not. We're calculating a Mandelbrot set. Some years I do Julia set, some days Mandelbrot set. It cuts down on code memory among the students. So, so the basic iteration is you're going to unpack this to scalar operations, and what you're going to build. We're going to talk about converting this to Verilog a little bit. But what you're going to build is a pipeline that calculates the new Z, checks for magnitude, and also checks to see if n is greater than n max. Calculates, uses, and then stores these guys and calculates the next round. So if you add this all up, you have, if you do this in the most obvious fashion, you have 1 multiplier, 2 multipliers, 3 multipliers, 4 and 5 multipliers. So you need 5 multipliers per pipe if you do them all in parallel. If you do a combinatorial calculation of this, you need 5 multipliers. Of course, you could break it down to 5 time steps and use 1 multiplier by building a state machine to step through the states you need to multiply. That way you get 5 times as many compute units, each running at 1/5 the speed, and you say, all right, so that's a wash, who cares? However, that may make a difference because there are 2 serial bottlenecks in this calculation. There's the first serial bottleneck is, what point do I start with? What is the value of CR and CJ for this new point? And more importantly, what value do you output to the VGA? And that is going to be serial because VGA is displayed from one serial memory block. Therefore, you have 1 read access or 1 write access per cycle on that memory block. And if you have a whole bunch of results that are all being calculated at the same time, they have to wait in line. So there may be an advantage to spreading out the calculation to cut down on, or staggering it to cut down on congestion on any given cycle.
Should each of these compute units be its own bus master and then let the have long bus? Who's writing the VGA memory?
Thank you. I think so. I think that you're probably going to want to organize this, that each one of these compute lines, which is going to be a fairly heavy calculation, it may run for 1,000 cycles. Maybe half the time will run for more than 5 cycles. You may want each one of these compute modules to have its own bus master and be able to write to the VGA screen independent of every other computational pipe. The big advantage of that is that way, hopefully, QSYS will handle the FIFO. That there will be a FIFO built if you, in fact, I know there is a FIFO on the VGA to help congestion when you're reading it out. An interesting question is, can you do enough writes to the buffer that you actually destroy the VGA display? You write with so many bus masters so fast to the bus that you overwhelm the bus bandwidth and stop the VGA display? And I think the answer is yes. I'm not going to let that worry me for this lab. If while you're calculating the display goes doink and then stabilizes again after the calculation is done, that is fine. If you were to do this as a final project where you want to be able to put on the VR goggles and zoom through the Mandelbrot set, then clearly you don't want to have this thing breaking up into pixels every time you do a calculation. Then you'd want to be able to synchronize properly the solver and the VGA so that you get good throughput and a stable display. But for this lab, if when you press calculate on the, or click on the mouse button to zoom in or zoom out, then, and the display flickers for 0.05 of a second, that's okay. So, you have 78 multipliers You have 78 multipliers, each one of which can do a 27 by 27 multiply. That's kind of a nice number. That's a good size number for this exercise. That way you could set this up as 4.23 notation. That's a reasonably good dynamic range. And if you needed 5 multipliers, that looks like about 15 pipes. That's a pretty good number. If you do the more or less trivial addition of keeping these results and reusing them on the next cycle, then the number of multipliers drops to 1, 2, 3. So if you reuse these two results for the next cycle, we don't have to do this or this. We do have to do this multiply. And so now you can get about 25 pipes. So optimized, you could probably get about 25 pipes fit onto this architecture. I don't think you're going to run out of logic elements. What happens when you hang 25 busmasters? I don't know. It may well be the case that building your own FIFO gives you better performance. There is a FIFO primitive that you can instantiate off of the intellectual property menu. You could mux in 20 different solvers in one cycle. Boom, boom, boom. You just drop them in. As soon as they're ready, you drop the results into the FIFO. And then the FIFO is the only bus master that interacts with the QBus abstraction. Maybe better throughput. I don't know. I don't have a good feel for what happens to the bus overhead with lots of masters. The fastest solve time we saw last year was about 35 milliseconds, so 0.035 seconds. And I'm sure some of you can guess who that was. It was two of your TAs. And about the fastest they could solve on the HPS was about 3 seconds. But there's other possibilities here. The HPS has on our box supports the neon vector arithmetic data set, which turns the processor into a 4-way vector arithmetic unit. I have no idea how good it is. The forums are mixed on this. Oh, it's great, it's horrible, it's slower, it's faster. I don't know. There's also, of course, 2 cores. You could run 2-way on the HPS. I'm guessing, though, that most people are going to want to build parallel hardware and get the advantage of the hardware acceleration. So one approach to this is you build a CPU. You build a CPU that only has 3 instructions. It has multiply, add, maybe subtract, and compare. And you build it so that it's native in fixed point notation. So that has the advantage then that you put the algorithm in assembly language, which you have to write, but might be faster to debug. It has the disadvantage that any CPU you build is going to have a 50% overhead because it has a fetch execute cycle. If you build a state machine rather than a CPU, there's no fetch cycle. Everything is an execute cycle so that you can save about half the time. So my guess is that most of you are going to build this as a fairly short state machine, maybe as little as 2 cycles if you're going to reuse multipliers. If you sequentialize, serialize, there we go, serialize, so you have to do 5 multiplies, then it'll take a minimum of 5 cycles. I've seen solution times on this anywhere from 2.5 minutes to, again, 30 milliseconds. The 2.5 minutes I don't expect to see anymore because that was using the old NIOS 2 microcontroller that was running at 50 megahertz. And the HPS is running 20 times faster than that, 19 times faster than that. So I would guess we're going to be down in the 2-3 second range maximum. The lab has some other requirements, not too many. You can use the HPS, but you don't have to. The corners of the region being plotted should be displayed either on the VGA, a serial console, or LCD display. That is to say, I want the coordinates in natural units. I want the a minimum of this corner C1 and this corner C2 so that you can tell where you are in the data set. And these are going to be fixed point numbers from plus or minus 1, plus or minus 2 in the x direction, plus or minus 1 in the y direction. System should compute, display the full Mandelbrot set. VGA graphics should run on the VGA at 640 by 480, blah, 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 8-bit color. I already talked about the log interface. Zoom interface using serial communication. There will be a zoom interface using serial communication to a terminal or mouse. There's another possibility, which I really don't suggest, and that is that you use 4 buttons on the board to move a cursor around on the screen and then press a button to choose a center. I think it's going to be more straightforward to use either a serial console on the HPS or to use a mouse attached to the HPS. If you want to attach a mouse to hardware, you're in a world of hurt if it's a USB mouse. Because the USB protocol stack is like that deep. And, but we do have some PS2 mice, which you can hook directly to the QSys bus and read out if you want to run a mouse directly from hardware. Given that you got to put formatted text on the screen, again, you probably want to use the HPS because you can use sprintf, you can use VGA text, all of the tools are there to make it work. So it's going to be easier. It's probably faster to do the timing on the HPS also. Easier to get a timer running on it. So this is a fairly heavy-duty example of a coprocessor that you would use to speed up a calculation on the HPS. It's you see, multiple copies is going to give you a significant speed advantage over the HPS, and so it could be a model for, say, scientific computation of a physical model, or maybe a pipe that would represent some sort of search engine running on the FPGA. Oh, I just saw an article in Hackaday. Somebody managed to train a neural net to compose music that sounds a lot like Bach. So they trained it on music for, a bazillion pieces of music for 8 hours. Anyway, you have to look it up. It could be fun to put on the FPGA. What do you think about this? I mean, what's the hard part here? The complex arithmetic? Nah. I think the hard part is figuring out how to divide up the work for all these pipes that you're going to build. Because somehow or another, you're going to have to say, who's doing this block? Who's doing that block of pixels? So you either have to hard code it, say, processor 0 is always doing the first stripe, processor 15 is always doing the last stripe. The only thing I'm going to send to each of the processors, the only thing I'm going to send is this corner and this corner. And then each processor knows what to do because they know their number. Which suggests that the processor is going to have a constant input for an identifier so it knows who it is. So you could do this. You could have a dispatcher that says, we've done this pixel, we've done this pixel, we've done this pixel, we've done this pixel. Who's going to do this pixel? I'm ready. Send a pixel off. So you have a queue of processors that have an open slot. You pick the first one in line, you give it a pixel, it iterates the pixel and returns a color to the VGA. And then says, I'm done, I'm ready for another one. The problem with that is that the overhead is tremendous because now you have to do 302,700 dispatches. You have to send data over 300,000 times out to pixels to do a 640 by 480 screen. And unless you're very careful, that becomes the rate defining effect. That becomes the rate limiting function. So maybe what you should do is send a whole line. You say, okay, you processor, you're doing that line. Or maybe you should send a block saying, I'm giving you these corners, you do it. Get back to me. It probably does not work to do dynamic load balancing where you would ask the processor, okay, you've done 10 pixels. How long did it take you on average? Because since the system is fractal, you cannot tell based on 10 pixels you can't predict the average of the rest of the array in that block. It could be, it has in fact a divergent standard deviation. It could be anywhere. So you probably want to do some sort of static system, whether you say, I'm giving you these corners, you do the work, or I don't care what the image is, you're taking the last 25 rows every time. Okay? Think about it. Come back on Monday with questions. See you in lab.